Going to solve a question on slope deflection method. So here's the question. Analyze the beam using slope deflection method. In this, here it is given a beam structure which is fixed on the both the ends and is having a hinge load in the center. So first we are going to solve this beam using a slope deflection method. So step number 1 is to find out degree of kinematic indeterminacy dk. So number of supports in which slope theta can occur is 1, which is theta b, because theta a and theta c are going to be 0 as the slope on the fixed end is 0. So therefore we have to find only one theta b. So step number 2 will be to find fixed end moments. So we are going to find fixed end moments at every span. So we are going to take span AB, here having moment, as we are going to find fixed end moments, we are going to name it MFAB. We are going to find from both side MFAB and MFBA. So MFAB is equals to minus WAB square upon L square, which is equals to minus 50 into D2 into 3 square upon 5 square, which is minus 36 kilonewton per meter. Minus sign is given because it is anti-clockwise. And from moment FBA, which is positive, so we are going to take WA square B upon L square, which is 50 into 2 square into 3 upon 5 square. As here the span is uneven, as the point load is acting in the uneven distance, therefore this formula is used. So next, for span BC, we fixed end moments MFBC is equals to minus WL square upon 12, which is minus 24 into 5 square upon 12, which is minus 50 kilonewton meter. And MFCB is equals to WL square minus 12 upon 12 is equals to 24 into 5 square upon 12 is equals to 50 kilonewton meter. The answer will almost be same, but the only difference is the sign, as it is anti-clockwise and it's clockwise. So next, step 3 will be to write down slope deflection equation. So for span AB, the slope deflection equation is moment AB is equals to moment at fixed end AB plus 2EI upon L bracket into 2 theta A plus theta B minus 3 delta upon L. So here we have previously found the fixed end moment at AB, which is minus 36 plus 2EI upon 5. Length of the span is 5, and EI, as in the question it is not given, we are going to keep it is as it is. 2, as we know theta A and theta C are 0, as the slope at fixed moments are 0, plus theta B minus, as the value is not given, we are going to consider it 0. So we get the equation, slope deflection equation for span AB, which is MAB is equals to minus 36 plus 0.4 EI theta B. So next, moment BA. Similarly we are going to find moment BA. Fixed moment BA plus 2 EI upon L, 2 theta B plus theta A minus 3 theta upon L. We are going to put values, and the final equation will be 24 plus 0.8 EI theta B, which is equation 2. And similarly we are going to do this for span BC. So moment BC is equals to fixed end moment BC plus 2 EI upon L bracket 2 theta B plus theta C minus 3 delta upon L. Going to put values, and the equation will be MBC is equals to minus 50 plus 0.8 EI theta B, which is equation 3rd. And similarly the MCB equation will be 50 plus 0.4 EI theta B, which will be fourth equation. Now moving forward to the step 4, apply equilibrium condition at joint. So applying it to the applying equilibrium condition at the joint B, we get the for this that MBA plus MBC is equals to 0. So from equation 2 and 3 we are going to put the values of moment BA and BC equation, and we are going to find the value of theta B, which is 16.25 upon EI. We have found the theta B. Now moving forward to step 5, put the value of theta B in equation 1, 2, 3, 4 and find the moments. So we are going to find the moments. So moment AB is equals to minus 36 plus 0.4 EI theta B. EI, so we are going to put the value of theta B, which is 16.25 upon EI, and getting EI cancelled and doing the addition and subtraction, we get the value of moment AB is minus 29.5 kilonewton meter. Similarly, we are going to find all the moments. Moment BA 37 kilonewton meter, moment BC minus 37 kilonewton meter, and moment CB 56.5 kilonewton meter. Now step 6 will be to find out support reactions. So for a span AB, we are going to doing the summation of moment at B. So MBA, we are going to take the moment MBA within point load 50, then converting into a moment by multiplying it into span, then minus moment at A, which is AB, which we have previously found, and putting the value, and the support reaction RA, which is this, and into multiplying the span is equals to 0. We get the value of RA, which is 28.5 kilonewton in the upward reaction. It is the support reaction at A. Then to find the support reaction at B, we are doing the summation of all the Y forces. Then RA plus RB1 minus 50 is equals to 0. We have find the value of RA. So putting the value, and we find the RB1 21.5 kilonewton upward direction. Then for span BC, similarly we are going to take the summation of moment at B, and using the summation at MB is equals to 0, clockwise positive direction, anti-clockwise negative direction, minus 37 plus 120 into 2.5 plus 56.5 minus RC into 5 is equals to 0. So we find the value of RC is 63.9 kilonewton. Then to find the support reaction at B, which is B2, we using the summation of all the Y forces, RB2 plus RC minus 120 is equals to 0. We get the value of RB2, which is 56.1 kilonewton. So we got two support reactions at B point. So we are going to sum it, and we get the support reaction at B, which is total 77.6 kilonewton. Then we are step 7 will be to find the shear force value. So we are going to take all the upward forces positive and downward forces negative. So for SF at A, just before A is 0, as we can see there is no forces, so 0 kilonewton. Then SF after A, which is the support reaction, we find it 28.5 kilonewton, as it is upward direction. Similarly, SF just before D is going to be similar to 28.5 kilonewton. SF just after D will be 28.5 minus, as there is 50 kilonewton downward direction, therefore it is minus, so we get the minus 21.5 kilonewton. So then similarly SF just before B, we answer is similar, 21 point, minus 21.5. Then SF just after D, which is including the support reaction at B, so we are going to add it and we get 56.1. Then SF just before C, you solving the UDL, we get as UDL is downwards, it is negative, so we are going to get the value of minus 63.9. Then SF just after C, just after C means support reaction at C, you solving this we get 0 kilonewton, it means we are going having the correct values. Then step 8 will be finding the bending moment values. So for free moment diagram we are going to find two bending moment values. So for free moment diagram, for span AB, using the formula WAB upon L is equals to 50 into 2 into 3 upon 5 is equals to 60 kilonewton meter. For span BC, WL square upon 8 is equals to 24 into 5 square upon 28, which is equals to 75 kilonewton meter. These formulas are different because of the condition, as BC is having UDL and AB is having point load but having uneven span. So for end moment diagram, and for end moment diagram we have already find the moments value, which is MAB minus 29.5 kilonewton, MBA 37 kilonewton meter, MBC minus 37 kilonewton meter, MCB is equals to 56.5 kilonewton meter. So now last step will be to draw the SFD BMD for this. So here is the SFD and BMD. So this is the question. This will be the SFD. We put all the SFD values and draw the SFD diagram. Then we have two BMD diagram, which are free BMD, which we have find the value by solving this 60 and 70 value. So we got here, as it is point load, it will be in a inverted triangle, and here UDL is there, so using a parabolic sign. Then fixed moment, here the values are this, and it's in the point load form, so we are going to get straight lines as it is fixed BMD. So now combining the both the BMD, we get this value, and we have kept this is positive value and this is negative, as it is negative value. So merging it, we get this value, this BMD. So here we have solved the beam equation using slope deflection method. Thank you.